Okay, so essentially what this is all about is me just going through the capstone activities with you in the organic worksheet and just overlaying some of my thoughts and sort of helpful tips on how to do these three things. So the first thing we're going to start off with this capstone activity, and I'm going to start with just explaining how do we do drawing a Lewis structure. And so like I've said many times before, I like to start by just reading it across, identifying the elements that can make more than one bond, drawing those first, putting in their valence electrons, and going from that. So I'm going to draw my carbons and my oxygen because they have got, as we know, 4 valence electrons each for my carbons, and I know that there are 6 valence electrons for my oxygen. I don't care how beautiful the dots are as long as they're all there. Next, I'm going to put in the hydrogens because they can only bond once. And so because they can only do that, I'm only going to put them in once. So to know where they're going to go, I'm first going to connect up everything that's going to bond to each other, right? Because this is a molecule. This entire molecule is called propanol. And so it's going to have to connect to itself first before it connects to a bunch of hydrogens. And when I see what's left, I see that the number of valence electrons left equates to the number of hydrogens there. Now, if that is not the case, consider that maybe there's a double bond going on between carbons or even a double bond between your oxygens. This, however, is not the case for propanol, so I can put in all my hydrogens in those remaining valence electron slots, and then I will have my molecule propanol. Again, be sure to correctly count how many carbons and hydrogens are there because I would hate for you to lose points if you were to put in a hydrogen that shouldn't be there, or say even put in a carbon that shouldn't be there. The same goes for when you're then relating it to, of course, a skeletal structure, because if your Lewis dot structure is incorrect, then your skeletal structure will definitely be incorrect. Okay. Next, how to identify important functional groups. So when I draw something like propanol like I just had before, or I draw something like ethene, we're going to look at what is there. And so first of all, I'm going to add in 2 groups that are not listed. One is an alkene, and an alkene is essentially just a double bonded carbon, which you might have seen before. And then also the final one that you need to know, which is alkyne, which is with a nice Y in the center. And that is for a triple bonded carbon. And those are the other 2 groups that you need to know besides the ones that are listed in this table that I would definitely take with you whenever you're going through and identifying functional groups. And the first thing I do is I literally just read through it like a list and check, do I see this group over here? And if so, then I'm good. And I like how this list is listed because it puts things like OH and then COOH. So in case I were to say see a carboxylic group, I might first circle this as being a alcohol, but then when I see the next one being carboxylic acid, I can go back and say, oh wait, the whole thing is carboxylic acid, so I can then go back and erase my previous statements about this being a carboxylic group, being an alcohol group, and then correctly identify it as in carboxylic acid. So again, reading through, I first start with this first molecule and I see alcohol and I circle my alcohol and I'm like, okay, that's the alcohol. There's no carboxylic acid, there's no ester, there's no aldehyde, there's no ketone, there's no amine, and there's no amide. So the only one that's in there is an alcohol group. The next thing I'm going to look for is, and there's no alkenes or alkynes. Next, I'm going to look at ethene, and the only thing on this list that matches with ethene is the alkene. So that is my alkene. Then when I go to the second structure, I see that we also have another alkene because I have a double bonded carbon, right? Because carbon is not going to show up on the skeletal structure. Now I'm going to go back to the top just because I see that there's more functional groups here, and I see that there's no OH connected to a carbon. There's no carboxylic acid. There's no ester. There's no aldehyde. There's no ketone. There is an amine, so we found one, so I found my amine, and there's no amide because there's no double bonded oxygen. The thing that I wanted to point out with this molecule, and I added it in for this reason, is that we've got this O group here, and it might be tempting to try and find one that closely fits or kind of fits what this would be, but the best thing to do is leave it. It's actually not a functional group that you need to identify in this exercise, and so it would actually be doing too much, and then you're going to find yourself being incorrect because you've identified something that isn't there. I especially recommend this for capstone activity number 4, where you're doing the functional groups of amino acids, because there are going to be a ton of things on there that you are just not been prepped to identify. Okay, now we're moving back into rate orders, and when we talk about rate orders, the first thing you had to do, I think you're going to remember back to your lab, is justifying the rate order that you identified. And this is something that a lot of people didn't completely justify, because the first thing that all of you got correct was it's the most linear, right? So when I look at these 3 graphs, I know this one is a 0, this one is a first, and this one is a second by looking at them, right? And then I see that this is the most linear, so I'm going to say ding ding ding, it's a first order reaction. I know my one looks really sad, so we're just going to pretend it's not there. But the reason why is that first order, and what you have to tell me then is it's first order because of the units. We're taking a unitless natural log of that concentration versus time and seeing a linear structure. So I need you guys to tell me the units of that graph, that you know that means first order, and that it's the most linear. Those 3 statements will get you full marks on the whole thing. That's where I need that going forward. Next, how do we write a rate law? Well, again, it's based on the equation just as much as it is on the graph, and not like we would think, right? Because when we think rate orders, we always said, oh, the coefficients don't matter, so why am I looking at the equation? But the more important thing from this equation is noting that this dinitrous pentoxide, or N2O5, is the only reactant. So when I see that the order that this matches to is in regard to the dinitrous pentoxide, and I see that that's the only reactant, it means that my rate is going to equal K times that concentration of the dinitrous pentoxide, but to 1, and that's it. That's the whole rate law, right? So that's something to be excited for. The next thing is finding K. So if you needed to find the value of K, you were going to relate it then to the slope of that line, right? Because the slope of that line, for when we're talking about first order, is going to equal negative K. And so I know that if I find the slope of this line, I'm going to find negative K. And to find the slope, I just have to do an algebra trick where I do y1 minus y2 minus x, or divided by, my x1 minus x2. And so I decided to take this at 3,000 seconds, because this is seconds times 10 to the third, and 0, because that's a simple one to find. And I see that this is about negative 3.3, and this, when I go over, is about negative 4.7, and that is what the natural log of the concentration equals. So when I'm plugging in these numbers up top, I am only plugging in the numbers from that intercept. I am not taking the natural log of them, because that would be incorrect. These numbers listed here are the natural log of the concentration. So if I were to go back and do the opposite and say e to those numbers, then I would get the concentration. But we don't want to go that way, right? That's not going to find me the slope. That's just giving me too much information. So then I just do the simple math here, and then I find that my slope, remember this is slope, is equal to this negative 4.82 times 10 to the negative 4. And I know that that is negative K, right? Because we're remembering from what that slope actually equals. So then I just divide by negative 1, and I get my K value that I've been wanting to know. And finally, how do I determine the units of that rate constant? Well, I see here that whenever I take the natural log of that concentration, it becomes something that is unitless. And so when I have a unitless structure, then the only unit I can count on for my K value will be what is in the denominator, which just so happens to be seconds. So that is why we get seconds to the negative 1, because it was in the denominator. If I were to be looking at, say, I went too far back. If I were to be looking at 0 order, I can see that I would have a unit up top. So my K would be meters per second, right? Because I can see that in the graph. The same thing here. I know that the concentration of this one, I would do m to the negative 1 times s to the negative 1. Or you could say 1 per m times s. These are two different ways to write that rate constant's units, but you get it from the graph. So the graph helps you find that all on its own. Okay, moving forward. back to the capstone activity number 4 now. So this one has the amino acids, and it's asking you to do things with pKa's and also identifying functional groups to kind of tie in that organic chemistry that you guys got to learn. And so these I put a little bit more complicated, right? Because amino acids are pretty complicated looking structures, so I thought I would add in a bit more complicated looking molecules. So again, I do the same thing. I'm gonna find my alcohols first, and I'm gonna circle them in black. And so I look through this first molecule, and I don't see any OHs. So I'm gonna move forward. Instead, I look at my second molecule, and sure enough, I have found an OH. So we're good to go. So the next thing I'm gonna do, if this will work, is I'm gonna find now the carboxylic acids. Carboxylic acids are going to look something like this. I'm going to draw in this H because this minus sign actually means that the hydrogen has been pulled off, but this right here is my carboxylic acid group on this molecule, so I'm going to circle that. I think in most of the activities that you do, it will show the hydrogen on it, so don't worry about having to remember to draw that in, but I just wanted to make sure you could see it on this molecule. Okay, and then the next thing I'm going to look for is an ester. So an ester is that double bonded oxygen to another oxygen off of that same carbon and then the rest of the molecule. And I don't see anything like that. So I'm not seeing anything like that. So again, there's no aldehydes, there's no esters. So then I'm going to look for aldehydes right here. And when I look for aldehydes, that's going to be a carbon double bonded to an oxygen with an H group. So you wouldn't actually see it, right? Like if we were to draw this in skeletal form, it would look something like this, where you wouldn't see anything, right? Because we don't draw hydrogens that are attached to carbons. So it would look like this. And I don't see any groups that end like that. So there's none of those. The next thing I'm going to look for is a ketone. And I find a few of them, right? I've got one here. This looks like a good ketone. This looks like a ketone. And this looks like a ketone. So far, so good. That's all looking good. Next, I'm looking for an amine. And I don't see any amines anywhere. This could be it. But then I realized something. This could be a secondary amine. So what I mean by that is because there's two hydrogens, that's a primary amine. If there was one hydrogen, so say this is bonded to a hydrogen here, and this is bonded to R, then this is a secondary amine. We go like this. And then, more importantly, if that nitrogen is actually just a single nitrogen, like this one, where it's only bonded to two R groups, then that is called a tertiary amine. It will look something like this. So, with that being said, if I were to look at this, I would say, wait a minute. I labeled these as ketones, but they're not ketones. They actually are this final group here, amides. Amides, we know, are the ones that have this nitrogen that's attached to the carbon that's double bound to an oxygen, which happens to be these groups. So this one right here is a tertiary amide, and this one right here is a secondary amide. So we've actually got two amides in here that were disguised at first as ketones. So this is what I was talking about before. You can find an alcohol, but if you find out later that that alcohol happens to be attached to, say, an C double bonded O, then you just erase it and draw your new one. So here we go. We have a tertiary amide and a secondary amide. And I'm emphasizing the pronunciation for you all. All right, skeletal structures. So when I'm looking for skeletal structures, the essential thing I'm looking for is who's important and who is not. And like I said in a previous recording, carbon and hydrogen, especially hydrogen bound to carbon, don't care. There's so many things that we draw in organic chemistry, and you will find out if you're taking an organic chemistry class. You're going to be drawing so many things. The last thing that organic chemists want to add on to that is drawing in the carbons and hydrogens that are going to overtake your structure. So the most important things to draw when you're drawing the skeletal structure are going to be the oxygens, the hydrogens that are bound to oxygens, and then of course sulfurs and nitrogens, anything that's not a carbon, a hydrogen, or a hydrogen bound to a carbon more specifically. So when I look at this first structure, this propane, or in this case it's butane because there's 4 carbons, you are going to see this and think, okay, how do I draw that then? Because there's only carbons and hydrogens, and I assume those hydrogens are going to be bound to those carbons. And so I'm telling you, the best thing to do is to start and count your carbons, right? Just like our Lewis structures. We're going to start with what we know is going to be connected. But instead, we know we don't draw carbon like we did with the Lewis structures. Instead, I put my pen down, I say that's 1 carbon. I move up, that's carbon 2. I move back down, that's carbon 3, and I move back up, that's carbon 4. The reason we don't draw them like this, where say we go from like Lewis structure to then skeletal structures, if I had to draw them linear, we don't know what that is. There's no thing. So the kinking or the bending of that backbone is just so we know how many carbons are in that line, right? So this is why we don't do that. So this is to show the carbons are there. And then remember, we don't drown the hydrogens, but when we see a carbon at the end, we can assume because carbon makes 4 bonds that it is bound to this 1 carbon. So that's 1 bond down and there's 3 bonds left, and those 3 bonds are going to correspond to these 3 hydrogens left. And if I move up to this carbon, I see that this carbon again has 4 possible bonds, but it is bound to 1 carbon here and it's bound to another carbon here. And so that means it has 2 spots left, and those spots are occupied by 2 hydrogens that we just haven't drawn in, because again, if we drew in all those hydrogens, that's going to take ages. Think about the Lewis structures you had to draw for the ethanol in Capstone activity number 3. That was a lot of drawing, and that was just for 2 to show the hydrogen bonds. Think of having to do it for more than that. It would just be insane. So next thing I'm going to draw is, again, I see 4 carbons, so I can already draw that similar backbone structure. But I see this new group, because I know here is CH3, I've seen that before, and CH2 and CH2, but this guy is just saying it's bound to 1H. And so if this carbon is bound to 1H, and there's an oxygen coming off the top, it's only bound to 1H. And here, if I were to count off my structure, right, carbon can bond to 4 things. And if carbon can bond to 4 things, but at this center right now, it's bound to 1 hydrogen, because we can see that written in this structure, in the condensed structure. And it's then only bound once to this oxygen. There's 2 bonds left, and that doesn't make much sense. So what we're going to draw in then, plus this 1 bond to that carbon neighboring it, and I have 1 bond left, and where that 1 bond goes is actually back into that oxygen. And so now we can see that the carbon is bound twice to that oxygen, once to its neighboring carbon, and then once more to a hydrogen that is not drawn. And that's why you see in this CH group, we've actually seen this before. This is one of our famous functional groups known as an aldehyde. And so an aldehyde has a carbonyl group, which we've seen before, that carbon double bound to that oxygen, but it has a hydrogen that is missing in action, and really that hydrogen is just not drawn, because again, like we said, drawing hydrogens on carbons, if we did that in organic chemistry, we would be drawing skeletal structures for years, because it would take so long to draw in every single little hydrogen in a perfect orientation. It would just take too long. Finally, I'm going to move on to my last structure, which I see again now 2 carbons. So I'm going to draw my 2 carbons. And then I realize, okay, so this guy is bound to, again, 1 other carbon. So that's 1 bond. And then it says it's bound to 3 hydrogens. So I can take off that. So that guy's fine. And then I see this carbon here. So this carbon, it's bound to 2 oxygens. Okay, so I draw in 2 oxygens here, like so. But then we have a problem, because it says it's not bound to any hydrogens. It's just bound to oxygens. And so when I read that off, I can say, okay, this hydrogen over here is bound to this oxygen, which is weird. And so now I have to say, okay, carbon has 4 bonds and only 3 are taken up. So who is the 4th? And again, it's just like we were doing with our aldehyde. We are adding a double bond to that oxygen, so that way that our carbon is now bound to 4 things and is perfectly happy. The reason we do not double bind it to this other oxygen is because that oxygen is already bound twice to hydrogen, and oxygen being 2 steps away from having 8 full valence electrons, being in group 6, right? Because we are always looking for 8 valence electrons. Because it's already bound to that hydrogen, it's not going to want to doubly bond to that carbon. And then when we look more closely at this COOH, we actually see that in another one of our well-known classes of organic compounds. That is going to be the RCOOH, which is our carboxy group, or a carboxylic acid. And so that's why sometimes that hydrogen you see is popping off in this structure, because it's an acid, so it likes to give up that hydrogen sometimes, especially in specific pKa solutions. Okay, so now moving forward, how do I order anything based on the strength when I'm talking about acids or bases when I'm looking at the pKa? And so we have to think back to what pKa means. And pKa just means the power of the equilibrium constant of that acid. So when I think about that, I have to think, okay, well, the stronger associating that an acid is, so the stronger it is, the less that it's going to dissociate. That means that when you think about the Ka expression, where Ka is going to equal that concentration of our conjugate base times the concentration of the hydronium ion, or H+, and we divide it by the concentration of the acid itself. The smaller that Ka value is, that means that the concentration of HA is larger. And the larger the concentration of the acid is, that means the less dissociating it is. So this means that really, if we have Ka being a super, super large number, then that means that it must be strongly dissociating, right? Because that means our numerator is now really big. And so that's why then when we look at the pKa value now, the smaller the pKa value, the stronger the acid. Because again, we're taking the log of that value, right? So we got to think in terms of math. So going forward now, the smaller the pKa value, the stronger the acid. I'm now going to say that this kind of makes sense when I look at these numbers, right? And we're going to go through it a little bit to make sure we're ordering them correctly. But I have hydrochloric acid having a pKa of -7, and so it makes sense that that's going to be my strongest acid. Not only is it one of the strong 7 that we always look at, but it's also got a pKa of -7, which is the smallest of the group here, and would be small in a normal group of different acids if we were looking at them. It just would depend, of course, you could see the pKa's of a bunch of strong acids, and then you'd have to really look at them. The next in line is going to be our protonated alcohol. The reason for that being is that, again, it has a pKa of -3. And so remember, when you're looking at strength in small, that when you're in the negative numbers, it's going to look a bit backwards. So the way that I look at this is, just remember, on a scale, you're going from -14 to +14, and the closer you are to -14, that means the stronger you are, and the closer to +14 you are, it means the weaker you are. And so that means that this protonated alcohol is actually slightly closer to +14 than -7, and so it's going to be weaker than HCl, but definitely not weak, because -3 is still quite strong for an acid's pKa value. Next, I have now positive numbers, but again, we just think of the same thing we were saying. The smaller the pKa value, the stronger the acid. The closer to 14, the weaker the acid. And so that means that next is going to be my aniline, which I'm just going to shorten to AN to save time. Aniline has a pKa of 4.6, so that's going to be the smallest of these three numbers. Next, I'm going to have pyridium. That makes sense because, again, it's 5.3, which is less than 9.2. And I end with ammonium, and ammonium is going to have a pKa of 9.2. But that makes a lot of sense if we think about it, because where does ammonium come from? Well, ammonium is just the protonated version of its base, its conjugate base, which would be ammonia. And ammonia is considered quite a strong base. And so when I think of a strong base, we know that strong bases have weak conjugates. So it makes sense to us in our brain that ammonium would have a weaker acid content and would have the higher pKa because it comes from a very strong base. So this makes sense to us. This list actually can compensate for our logical thinking when we think about acids and bases that we've learned before. Okay, moving on to Bronsted-Lowry versus Lewis acids and bases and conjugates. And so basically what I'm going to go through is these ones are going to be our Lewis acids and bases, and these ones are going to be our Bronsted-Lowry acids. So when we think about a Bronsted-Lowry acid, we always think of donating a proton. Who is going to be giving away a proton? So when I look at one side and compare it to its conjugate on the other side, the conjugate should have one less proton than before. And then with a Bronsted-Lowry base, this is one that accepts a proton. And so when it's accepting a proton, this means that when I go from one side of the equation, I find its conjugate on the other side, and it should have another proton on the other side. Sometimes this is hard to see, so we're going to go through it in detail. So first, I'm going to circle or underline the two species that are matching up on either side, because that's, of course, the first thing that's very important. So when I look at these species, I say that these are the ones that have similar components, and so they are probably the ones that are going to be together. And then I look at the same thing here. I say that these are probably the ones that are going to be together, and these ones are probably going to be the ones that are together. So that's fine. And then I'm going to go through who got a proton and who accepted a proton. Or sorry, who got a proton, who gave away a proton. So when I look at NH3 to NH4, it went from 3 protons to 4 protons. And so that means that it gained a proton. And by gaining, it means it accepted. So this is going to be my base, and this is going to be my conjugate acid. And then when I look at water, I see that it went from 2 hydrogens to 1. And so this means it gave 1 away. And so this is my acid, and this is my conjugate base. Moving on to the second one, I have water. It goes from 2 protons to 3 protons. So that looks like it got a proton, so it accepted one. So this is probably my base, and this is going to be my conjugate acid. And then when I look at HCl to Cl minus, it went from 1H to 0. So it obviously gave away 1. So this is going to be my acid, and this is going to be my conjugate base. Now, moving into Lewis acids and bases, when I think about a Lewis acid and a Lewis base, I automatically can look back to even previous examples, and you're going to find that the answer is going to be the same. So a Lewis acid is a species that accepts an electron pair, and when you think about that, accepting electron pair would make the species more negative. So this is kind of going back into our redox brains, where we were thinking about things that became more negative. Does that make it positive or negative? You know, counting off its oxidation states and stuff like that. So this is going to come in handy there. Lewis bases donate an electron pair. And so if they get rid of an electron pair, they're going to become more positive on the other side, right? So when I look at this equation here that I've already mapped out, I can say this went from being neutral water to negative OH minus. And so that would also make this an acid by Lewis standards, because it went from 0 charge to -1 charge, which makes it more negative, right? Because it accepted an electron pair. And then when I look down here, and I'm going to put dots here because this looks like oxidizing agent, so I want to make sure we're clear that this is 0. And then I can look at this one as well. This went from something that was neutral to something that has a +1 charge. And again, that's because it donated electron pairs. And so this is going to be a base. Now, we can look at that again in a more oxidizing sort of perspective, and that will help us as well. So if we think about it this way, this is going from +1 and -1, and this is +1 and -1 here. And we see on this side, so if I look already at Li, it's still going to be plus and minus. So this seems to be the spectator ions that don't mean much. But this one is 0. Everything in here equals to 0. And so when I think about that, I think, well, wait a minute. I just have to look at this in reverse. So this H became positive. And so this went from positive to 0. So this became more negative, right? Because if I go from +1 to 0, that means it had to become more negative. So this is going to be my Lewis acid. And then if I look at this went from negative to 0. So -1 to 0 would then mean I became more positive. So this is going to be my base. So that is how we would work with Lewis acids and bases. Just remembering that redox stuff that we just did, these become a lot more simple. And so here I see that zinc is 0, right? Anytime it's a metal, all by itself, it's 0. And then on this side, it becomes +2 because that Cl is actually -1, but there's 2 of them. And then this H2 is 0. It's a gas and it's diatomic, so it's itself, but this one is +1. And so when I look here, I went from 0 to +2, so that's obviously becoming more positive. And so when it becomes, again, more positive, this is going to be a base. And then this went from +1 to 0, so that means it got more negative, right? Because if we're +1 down to 0, we must have subtracted 1. So this must be my acid. Great. So hopefully you can rewatch this section and it'll make a little bit more sense in case that was not doing it well. But also I hope this explanation more solidified your understanding of acids and bases for Lewis acids and bases. Next, we're doing an ice table. And in your capstone activity, please note that you have some conjugate base and acid. So you can either do the Henderson-Hasselbalch equation or you can do an ice table. I do an ice table because I find ice tables keep my understanding of X's understood. But if you want to do the Henderson-Hasselbalch equation, feel free to do so. All of that works out the same because, again, you know the concentration of your conjugate base and you know the concentration of your acid. So this is a disclaimer. So first things first is I look at my change here and I say, okay, I've got an initial of 0.2 plus 0 versus 0.7. So this one has more. So I'm going to subtract X on this side and add X onto this side. So this means at equilibrium then that this is going to be 0 plus X. This is going to be 0.2 plus X, and it's going to be 0.07 minus X. Then when I plug that all in, so I know that first I need to take my pKa value. So again, you're looking for the pKa1 of threonine, so please make sure you're looking at the right pKa, and you're going to take 10 to the negative pKa, and that is going to equal your Ka value, right? So if I have my Ka value, I just set that equal to the concentration of my conjugate base times the concentration of my hydronium ion divided by the concentration of my acid. And then I'm going to split that up into two different fractions, because that's how that works, and then multiply this to get rid of that denominator by 0.7. I realized by the 5% rule I no longer need this minus x because it would be canceled out, so I do 0.07 multiplied by both sides, and then I solve for x, and I would get x equals 6.34 times 10 to the negative 5. I then know that this is equal to my concentration of my hydronium ion, so I know that in order to find my pH, which again is what they're asking for, same in the capstone, please don't stop here, continue on to find the pH. You take the concentration, take the negative log of that concentration, and you will get your pH value. So please rewatch this section if you don't want to use the Henderson-Hasselbalch equation, and if you do, please feel free to send on your work and ask me if things look a bit screwy or not. All right. The organic chemistry worksheet. So when we're looking at the organic chemistry worksheet, the one thing we're doing is we're asking, how do I write a condensed structure? How do I write a skeleton structure? How do I write a chemical formula? And then finally the name, which a lot of people are really anxious about naming something. I would say the best bet with this one is, if you are feeling anxious about your name, is to simply Google it and see if the name that you've come up with exists. And if it doesn't, then type in the condensed structure, and you're sure to find a possible structure that maybe looks a bit more like what you were thinking, especially with your skeletal structure, okay? So this one, I know because it has 2 carbons is going to be ethane. And so with that, I would say, okay, my skeletal structure is, I put my pen down for 1 carbon, and I put my pen up, and then that's the 2nd carbon, and we're done. That's how simple ethane is. It's only 2 carbons. I know that carbon is again bound to 4 things. It's bound to 1 carbon on each side, so each of them has 1 bond done, and then it should have 3 hydrogens on either side, so it's perfectly drawn. Great. Next, I'm only given the skeletal structure. So when you're only given the skeletal structure, the best thing to do is start with the condensed structure, I feel, because that one gives you an overall vibe. So I start with this carbon on this side, and I see that it is bound to 3 hydrogens, because that's what it means when the carbon is at that end. I then go to the middle carbon, and I see that it's bound to 1 hydrogen, and then it's also bound to alcohol group. And then that carbon is then bound to another carbon, and that carbon is bound to 3 hydrogens. So that is that sorted. The next thing I'm going to do is I look at the chemical formula, and I say, okay, the chemical formula is essentially just this rounded up and added together. And so if I go 1, 2, I have 3 carbons. So 3 carbons here. And then I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that's fine. And then I have 1 oxygen. Okay. Now, naming this guy. This is where people, of course, get really scared. I'm telling you, you don't have to be scared. So the first thing is, whenever you see an alcohol, that is going to end in OL, because alcohol. And then the other thing is noting where that alcohol group is. So when I'm counting off, I only count off the number of carbons. I go 1, 2, 3. So I see on 1, 2, on that 2nd carbon, that is where the alcohol is. And so I'm going to put a 2 there, because that is where the important group is. So I'm letting someone know, at carbon number 2, we branch off into something else. There's something different. Then, if you look down to propane, and you see you got 3 carbons and 8 hydrogens, just like up here, that is your clue to say, okay, the root of this then must have propane. And so that is how we name these. We just kind of go on roots. And so actually it is propanol. And then that is the name of this structure, 2-propanol. If you had 1 propanol, it would mean that the oxygen would be on this end, which is exactly what if I go all the way back to the very, 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 very beginning, that is what this is. This is propanol, which, because we say propanol, we assume it's 1 propanol, but if it were 2 propanol, that oxygen would be up there. So this is all kind of tying together. Whoop. Next, I'm going to do 3-mental pentane. So again, pent means 5. If you think pentagon, it's the same idea. And so I draw 1, 2, 3, 4, 5. Then I say at carbon 3, there's a methyl group. And methyl group is this group like here on this end, this CH3. So I go 1, 2, 3, and I draw my methyl group. If it said ethyl, which would be for ethane, then we would have another line here, because ethane means there's 2 carbons, methane means there's 1 carbon, which we'll find out later when we're talking about these. So, with that being said, everything should be quite simple, right? Once we have a skeletal structure, we know what's going on. I have 1, 2, 3, 4, 5, 6 carbons, so I can say carbon 6. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Great. And then if I need to do the condensed structure, I just got to name it as I did with my 2-propanol. So I start off with that CH3, that's pretty common. I move on to my second carbon, which is CH2, so that's still pretty good. And then I move to that third carbon, which is just CH, because remember, carbon has to be bonded to 4 things. And then we don't draw any lines because in the condensed structure, we only take into account oxygens or nitrogens that are special. But in this one, we'd go down now and say CH3. And then we go back up, and the next carbon in line is this CH2, and then we finish off with that final carbon, which is a CH3. Great. All right, and the last order of business is drawing propane, and when we draw propane, we essentially just say to ourselves, okay, I do exactly as I did up here for ethane. I have 3 carbons, so 1, 2, 3. And there we go. That's all of them, and all of them have their accounted for structure. Okay. Organic chemistry, hydrocarbons. So when we're talking about hydrocarbons, we're specifically talking about natural gas being the number 1 way that we release hydrocarbons into our atmosphere. The number 1 released natural gas form of a hydrocarbon is methane. This is something that not only rudimentary animals like cows and sheep release when they process their gases in their 4th stomach when they're eating things like grass or tough sheet grass, but also things like termites will release this when they are chewing through wood. And as well, we see other ones moving down as we get to more complex structures like decomposing plant material. So when you have plants dying off, they are releasing ethane. And then also ethene, which is from ripening fruit, which is why they tell you not to put your bananas next to any other fruits, because as they are ripening and becoming more yellow, they are actually dying, and they're not dying, but they're breaking down their carbon, and they're releasing ethene, which then likes to attach onto other plants and influence them to also do the same, which is ripen when they might already be quite ripe. So that's why we don't do that. So number 1 is methane, number 2 is ethane, and number 3 is ethene. And these are the 3 that are the top 3 that are released, methane being the most. And it's all of them are coming usually from natural gas that is released, especially in things like coal mining, because coal is primarily carbon. And again, carbon likes 4 bonds. So moving on, identifying isomers. Again, the one thing is they should have the same chemical formula. So if we remember what the chemical formula is, it just means this. It doesn't mean the condensed structure. So as long as it has the same number of carbons, same number of hydrogens, same number of oxygens, etc., those will all be isomers. So these ones seem to all be carbons and hydrogens. So that makes this a little difficult, but not too difficult. So the first thing I'm going to do to rule out any non-isomers is just count up the carbons. That's the most easiest thing to count. So I go 1, 2, 3, 4, 5, 6. So this guy has 6 carbons. 1, 2, 3, 4, 5. This guy has 5 carbons, so he's already probably not one of the isomers. 1, 2, 3, 4, 5, 6. Okay, so it seems these 2 are possibly isomers. And then 1, 2, 3, 4, 5, 6. So this guy's possibly an isomer. So these all have 6 carbons. This guy has 5 carbons, and this guy has 6 carbons. So this one's definitely not an isomer. The next thing to do is find the hydrogens. You want to make sure that it is a true isomer and not one that kind of looks like an isomer. So the way that we're going to do that is we're going to count up the hydrogens that are on there. And remember, hydrogens bond to carbon to fill in the gaps that carbon's already bound to. So like these carbons only have 1 hydrogen on them. So 1, 2, and then these have 3 on them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this guy is 14. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this one has 14 hydrogens. And this last one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So there we go. So these are all going to be isomers, but notice they have the same formula. Make sure you count the hydrogens and make sure you understand how to count those hydrogens. Remember, hydrogens like to bond to carbon to fill in the gaps of carbon not being already bound, and oxygen likes to take on a hydrogen if it's only bound once to something else. Finally, doing a more functional group practice. So this is the last part of your sheet. This is where we look at something that's a little more complicated. I'm looking at something called ATP. ATP, of course, you know, likes to power a lot of chemical reaction processes in our cells. It also happens to make up a part of our backbone in our DNA. It's the adenine base pair when we get rid of those phosphates. And also we deoxygenate that ribose sugar that's in this center here. So we like to cut these guys off at the leg, and it becomes a beautiful base pair that can hydrogen bond with the thymine on the other side and or uranine, depending on if it's RNA. So the next thing we're going to do is we're going to identify the alcohols in this group. So if I look down here, I can say there's one alcohol here and there's one alcohol here. There's an alcohol here, here, and here. Notice that here it doesn't say this has to be carbon, it just says it has to be bound to something. Next, a carboxylic acid. Now this one specifically states that the carbon must be double bound to that oxygen. So it's tempting sometimes when you see this phosphate group to assume that this might be a carboxylic acid, but actually it's because it's the phosphorus that's in that center that makes it not a carboxylic acid, because that carbo actually is for carbon. And so this doesn't have a carbon at the center of that. So that would be a incorrect identification of this. So this is not a carboxylic acid. So we have no more carboxylic acids in this group. Next, I move on to the esters. And so an ester is going to have, again, a C double bound to an oxygen, double bound to another oxygen. So again, these are not esters because there's a phosphorus in the center, so I don't see any other esters in this group. And then when I go back through, I say, okay, how about aldehydes? And when I look for aldehydes in this group, I don't see any aldehydes. Next is looking for ketones. So when I look for ketones, I don't see any ketones in this group because, again, this needs to be double bound to a carbon, and there's none of that. Next is looking for amines, and so sure enough, I see a nice amine right here. This is a beautiful primary amine. This actually is the thing that helps hydrogen bond to that thymine and make a beautiful one of the double bonded one of the two hydrogen bonds to our thymine group. And then finally, I'm looking for amides, and there is no amides in this structure, so I can say without a doubt that we pretty much have labeled everything in our ATP. Next, we move on to our bottom structure. I drew this from my brain, so I have no idea if this exists, but bear with me. I'm hoping it will highlight some structures for you. So first we have an alcohol group that's listed off the very bat. Next, do we have any carboxylic acids? I do not see any. When I look here, this could be it, but then I see that this is bound to a carbon and this is a carbon, so this does not satisfy the carboxylic acid, but I do see that it satisfies my ester. So this is my ester group because, again, it's a carbon double bound to an oxygen and then bound to another oxygen that's bound to another R group, or carbon in this case. Next, I move on to aldehydes. I don't see any aldehydes in this group. Those seem to be missing. Then I move on to ketones, and sure enough, I do find a wonderful ketone right here at the top of this pentyl group, and that looks really nice. Next, I look for amines, and sure enough, I find a beautiful amine right there. So I get a genta out. This is a primary amine, perfect for hydrogen bonding. And then if I want to go one step further, I could say I also have an alkene right here. So this is my alkene. If you wanted to label everything in this, that's an alkene. Great. So that's all of the functional group process, and that ends our discussion of this worksheet. If you have any questions, please feel free to ask me. If you have anything that you wanted help with, please feel free to email me. And with that, I hope you have a wonderful rest of your dead week. Please remember to hydrate, eat 3 meals a day, go outside for a little bit. Today's maybe not so gloomy, but the weather should still be nice, so that's good. Have a wonderful week, and I'll see you guys later. Bye. Discard that.